Hello, my dear, and welcome to our astronomy course. Today, we are continuing study galaxy. And so we will be continuing the previous topic, Milky Way galaxy. Just as paleontologists reconstruct the history of life on our planet Earth from the fossil record, astronomers try to reconstruct our galaxy's past from the fossil it left behind as it formed and evolved. That fossil is the spherical component of the galaxy. The star in the halo formed when the galaxy was young, and so their chemical composition and distribution provide clue to the birth of whole galaxy. To begin, you should ask yourself how old our galaxy is. That question is easy to answer because you already know how to find the age of star cluster, right? But there are uncertainties that make the easy answer hard to interpret. The oldest open clusters in our galaxy have ages of about 9 billion years. These ages are determined by analyzing the turn-off point in the cluster HR diagram. But three main things make these ages uncertain. First, finding the age of a star cluster becomes more difficult for older clusters because they change more slowly. And also, the location of their turn-off points and giant regions depend on the chemical composition, which can differ slightly from cluster to cluster. And finally, open clusters are not strongly bound by their own gravity. So there may have been older open clusters that dissipated as their stars wandered away. But in any case, from open clusters, you can get a rough age for the disk of our galaxy of about 9 billion years. Globular clusters have faint turn-off points in the HR diagram and are clearly old, but finding their ages is difficult. Clusters differ slightly in chemical composition, which must be accounted for when calculating the stellar model from which ages are determined. And also, to find the age of a cluster, astronomers must know the distance to the cluster. And globular clusters are too far away to have measurable parallax. The Hipparcos satellite has, however, measured precise parallaxes for Cepheid variable stars. And that has improved the calibration of these distance indicators. I hope you remember what I'm speaking about. Okay? So, in addition, careful studies with the newest large telescope have refined the HR diagrams of globular clusters. Globular cluster ages seem to average about 11 billion years. There is still some uncertainty in the measurement of ages, but some clusters do seem to be older than others. The oldest are a bit over 13 billion years old. So the halo of our galaxy must be at least 13 billion years old, right? And the ages of star cluster tell you that the disk is younger than the halo and show that our galaxy, as I recently mentioned, at least 13 billion years old. Now, you can combine these ages with subtle differences in the chemical composition of stars to tell the story of our galaxy. In the 1940s, astronomers realized that there are two types of stars in the galaxy. The stars that are closest, brightest, and most easily studied are located in the disk. These are called population first stars. The second type are much more distant, fainter, and are found in the halo, in globular cluster, or in the central bulge. They are called population two stars. It is significant that the two stellar populations are associated with the two components of the galaxy. Logically, right? The stars of the two populations are very similar. They fuse the same nuclear fuel and evolve in nearly identical ways. They differ only in their abundance of atoms, heavier than helium. Atoms that astronomers refer to collectively as metals too. But note that this is not the way the word metal is commonly used by nano-astronomers. Population 1 star, a metal rich containing 2 to 3% metal, while population 2 star, a metal poor containing only about 0.1% metals or even less. The population membership of star is defined by its metal content and not by its location in the disk or spherical component. Population 1 star belong to the disk component of the galaxy and are sometimes called disk population stars. They have circular orbits in the plane of the galaxy and are relatively young stars that formed within the last few billion years. The Sun is a population first star. Population 2 stars belong to the spherical component of the galaxy and are sometimes called halo population stars. These stars have randomly tipped orbits with a wide range of shapes. A few follow circular orbits, but most follow elliptical orbits. The population 2 stars are all lower mass main sequence stars or giants. They are all stars. The metal poor globular clusters are part of the halo population. You can now understand why there are two kinds of Cepheid variables shown in the period luminosity diagram, as you can see in this slide. Type 1 Cepheid are population first stars with metal abundance similar to that of the Sun. The type 2 Cepheids are population second stars. The difference in metal abundance affects the opacity of the gas, and thus the ease with which radiation can get through. And that changes the balance between gravity and energy, flowing outward through the star. A few percent difference in metal abundance may seem like a small detail, but it makes a big difference for stars. Since the discovery of stellar population, astronomers have realized that there is a gradation between populations. Let's look to this table. The most metal-rich stars are called extreme population 1 star. Slightly less metal-rich population 1 star are called intermediate population 1 star. The Sun is such a star. Stars even metal-rich, such as the stars in the nuclear bulge, are intermediate population 2nd star. The most metal-poor stars are those in the halo and in globular cluster. They are extreme population 2nd star. Why do the disk and halo stars have different metal abundances? They must have formed at different stages in the life of the galaxy. At times when the chemical composition of the galaxy differed. This is a clue to the history of our galaxy. But to use the clue, you must discuss the cycle of element building. Okay? The atoms of which you are made were created in a process that spanned a number of generations of stars. Natural processes are all around you, and you must learn to recognize and understand them if you are to understand nature. The process that builds the chemical element may be one of the most important processes in the history of our galaxy. When you study the evolution of giant stars, you learn how small amounts of elements, heavier than helium, the elements astronomers call metal, are cooked up during helium fusion. Additional heavy atoms are made by short-lived nuclear reactions that occur during a supernova explosion. When stars die, small amounts of these elements are spread back into the interstellar medium. Low mass atoms like carbon, nitrogen, and oxygen are common. But atoms significantly more massive than iron, such as gold, silver, platinum, and uranium, are rare because they are made only during supernova. Okay? Are you agree? Now, this figure shows the abundance of the chemical element. This graph is usually drawn with an exponential scale as in the part of the figure. To get a feeling for the true abundance of the element, you should draw the graph using a linear scale as in the right figure. Then you see how rare the elements, heavier than helium, are. Compare hydrogen, helium, and bottom you can see all the rest in the galaxy: carbon, nitrogen, oxygen, and even fire. When the galaxy first formed, there should have been no metal because stars had not yet manufactured any. Okay? The gas from which the galaxy condensed must have contained about 90% hydrogen atoms and 10% helium atoms. The hydrogen and helium came from the Big Bang. Remember, that began the universe, which you will study in a later. The first stars to form to form from these gas the metal core. The more massive stars died, and now 13 billion years later, only lower mass stars are left with spectra that show few metal lines. Of course, they may have manufactured some atoms heavier than helium, but because the star's interior are not mixed, those heavy atoms are stayed trapped at the centers of the star, where they were produced and do not affect the spectra. Let's look at this diagram. The extreme population 2 stars in the halo are the survivors of an early generation of stars to form in the galaxy. Most of the first stars evolved and tied, enriching the interstellar gas with metals. Succeeding generations of stars formed from the gas cloud that were enriched, and each generation added to the enrichment. By the time the sun formed, it was roughly 5 billion years ago. The element building process had added about 1.6% metal to the interstellar medium. Since then, the metal abundance has increased further, and stars forming now incorporate 2 to 3% metal and become extreme population, the first star. And thus, metal abundance varies between populations because of the accumulation of heavy atoms produced in successive generations of stars. The lack of metals in the spherical component of the galaxy tells you it is very old, a fossil left behind by the galaxy when it was young and drastically different from its present disk shape. The study of element building and stellar populations leads to the fundamental question: how did our galaxy form? In the 1950s, astronomers began to develop a hypothesis to explain the formation of our galaxy. Recent observations, however, are forcing a re-evaluation of that traditional hypothesis. The traditional hypothesis said that the galaxy formed from a single large cloud of gas over 13 billion years ago. As gravity pulls the gas together, the cloud begins to fragment into the smaller cloud. And because the gas was turbulent, the smaller cloud had random velocity. Stars and star clusters that formed from these fragments went into a randomly shaped and randomly tipped orbit. These first stars were metal pure because no earlier stars had existed to enrich the gas with metal. Some of these stars remain as the population 2 stars observed today in the halo. The contracting gas cloud was roughly spherical at first, but the turbulent motion cancels out, as do eddies in recently stirred coffee. Remember, you may model this mnemonic, leaving the cloud with uniform rotation. A rotation, a low-density cloud of gas cannot remain spherical. A star is spherical because its high internal pressure balances with its gravity. But in a low-density cloud, the pressure cannot support the weight. Like a blob of pizza dough spun in the air, the cloud had to flatten into the disk. Look at this, especially right part of this slide. And this contraction into a disk took billions of years, with the metal abundance slowly increasing as generations of stars were born from the gradually flattening gas. The stars and globular clusters of the halo formed by the cloud when it was spherical and were left behind. And subsequent generations of stars formed in a flatter distribution. The gas distribution in the galaxy now is so flat that the youngest stars are confined within these only about 100 parsecs deep. These stars are metal-rich and have nearly circular orbits. This traditional hypothesis accounts for many of the Milky Way's properties. Advances in technology, however, have improved astronomical observation, and beginning in the 1980s, contradictions between theory and observations. For example, improved observations show that globular clusters have a range of ages, but the traditional hypothesis suggests that the globular clusters should have a roughly similar age. Also, some of the oldest stars in the galaxy are in the nuclear bulge, not in the halo. But the theory says the halo formed first. And furthermore, the oldest clusters in the disk are much younger than the halo. But the traditional hypothesis suggests that star formation was continuous as the galaxy flattened. New observations show that some halo stars are even more metal than the globular cluster. So those stars must have formed before the globular cluster. Are you agree with me? And also, even the most metal-pure stars in the halo are not metal-free, and so there must have been a generation of stars that manufactured those metals before the halo formed. The traditional hypothesis says nothing about those first stars. Can the traditional hypothesis be modified to account for these observations? Perhaps the galaxy began with the contraction of a gas cloud to form the central bulk, and the halo formed slightly later from infalling clouds of gas and stars that had been slightly enriched in metals by an early generation of massive stars. That first generation of stars would have formed from almost pure hydrogen and helium gas, which would have been so transparent to energy that the stars would have formed with high mass. Those stars would have lived very short lives, so none would be left today. The metals they made during their short lives would explain the metals observed in the oldest stars. Observation made as part of the Sloan Digital Sky Survey have allowed astronomers to compute the motions of over 20,000 halo stars. And those motions reveal that the inner part of the halo, closer than 50,000 light years, the center, and has a gentle rotation in the same direction the sun orbits. But the outer halo tends to rotate in the opposite direction. The stars in these two regions also have slight chemical differences that suggest that the halo was built gradually as smaller clouds of gas and stars fell together. The disk could have formed later as the gas that was already in the galaxy flattened into a disk. And as more gas fell into the galaxy and settled into the disk, perhaps entire galaxies were captured by the growing Milky Way galaxy. You will see in the next lecture that such mergers do occur. If our galaxy absorbs a few small but partially evolved galaxies, then some of the globular clusters in the halo may be hitchhikers. And this would explain the range of globular cluster aging. Astronomers are slowly puzzling out of mystery of our galaxy's origin. And they are also solving the mystery at the center of Tau. And now let's come to scientific argument. Why do metal queer stars have the most elongated orbit? A good argument makes connections between ideas, and sometimes those connections are not obvious. So the metal abundance of a star cannot affect its orbit. So an analysis must not confuse cause the effect with the relationship between these two factors. Both chemical composition and orbital shape depend on the third factor, age. The oldest stars are metal queer because they formed before many stars could create and scatter metals into the interstellar medium. Also, the oldest stars formed long ago when the galaxy was young and motions were not organized into a disk, and they tended to take up randomly shaped orbits, many of which are quite elongated. And secondly, today, the metal queer stars tend to follow the most elongated orbit. But nevertheless, even the oldest star known in our galaxy contains some metal. They are metal queer, not metal free. Adjust your argument. Where did this metal queer star get their metal? How is it? Another subtopic today's lecture, the nucleus. The most mysterious region of our galaxy, it is very center, the nucleus. At visual wavelength, this region is totally hidden by the gas and dust that dims the light it emits by 30 magnitude. If a trillion photons of light left the center of the galaxy on a journey to Earth, only one would make it through the gas and dust. The longer wavelength infrared photons are scattered much less often. 1 in every 10 makes it to Earth. And consequently, visual wavelength observations reveal nothing about the nucleus, but it can be observed at longer wavelengths, such as in the infrared and radio parts of the spectrum. Harlow Sharp's study of globular clusters placed the center of our galaxy in Sagittarius, and the first radio map of the sky showed a powerful radio source located in Sagittarius. Infrared waves detected an intense flood of radiation coming from the same source, and higher resolution radio maps revealed a complex collection of radio sources with one Sagittarius A. Sagittarius A is star, abbreviated Sagittarius A star, and usually pronounced Sag A star. Sag A star, okay? Lying at the expected location of the galactic core. High-resolution observations made with the VLBA, the radio interferometer that stretches from Hawaii in the Pacific to the Virgin Islands in Atlantic, and show that SRGA star is no more than one astronomical unit in diameter, but it is a powerful source of radio energy. What could be as small as Sagittarius A star and produce so much energy? This is question that maybe namely you or your mate could do. Study Sagittarius A and notice three important points. First, observations at radio wavelength reveal complex structures near Sagittarius A star, caused by magnetic field and by rapid star formation. Supernova results show that massive stars have formed there recently and died supernova death. Second, the center is crowded. Tremendous number of stars keeps the dust and produce strong infrared radiation. And finally, there is evidence that Sagittarius A star is a supermassive black hole into which gas is flowing. A supermassive black hole is an exciting idea, but scientists must always be aware of the difference between adequacy and necessity. A supermassive black hole is adequate to explain the observation, but is it necessary? How do you think? Could there be some other way to explain what is observed? For example, astronomers have suggested that gas flowing inward could trigger tremendous bursts of star formation. Such theories have been considered and tested against the evidence, but none appears to be adequate to explain the observation. So far, the only theory that seems adequate is that our galaxy is home to a supermassive black hole. Meanwhile, observations are allowing astronomers to improve their model. For instance, Sagittarius A star is not as bright as in X-ray as it should be if it has a hot accretion disk with matter constantly flowing into the black hole. Observations of X-ray and infrared flares lasting only a few hours suggest that mountain-sized blobs of matter may occasionally fall into the black hole and be ripped apart and heated by time. But the black hole may be mostly dormant and lack of fully developed hot accretion disk, because little matter is flowing into it at the present time. Such a supermassive black hole could not be remains of a single dead star. It contains much too much mass. It probably formed when the galaxy first formed over 13 billion years ago. The center of our galaxy is mysterious because it is hard to observe and hard to understand. And similarly, the spiral arms of our galaxy have given astronomers a challenging path. studies of other galaxies show that spiral arms contain hot blue stars. And thus, one way to study the spiral arc of our own galaxy is to locate these stars. And fortunately, this is not difficult, since O and B stars are often found in associations and being very bright, are easy to detect across great distances. But unfortunately, at these great distances, their parallax is too small to measure, so their distances must be found by other means, usually spectroscopic parallax. The O and B associations visible in the sky are not located randomly, but fall along paths of three spiral arcs near the Sun, which have been named for the prominent constellations through which they pass. Look at this slide. If you could penetrate the cars and stars, you could locate other O and B associations and trace the spiral arms farther. But like a traveler in a fog, you see only the region nearby. Objects used to map spiral arcs are called spiral traces. O and B associations are good spiral traces because they are bright and easy to see at great distance. Other traces include young open clusters, clouds of hydrogen ionized by hot stars, because we have emission nebula, and certain Cepheid variable stars. Notice that all spiral traces are young objects. All stars, for example, live for only a few million years. If the orbital velocity is about 200 up to 250 kilometers per second, they cannot move more than about 500 per second in their lifetime. This is less than the width of a spiral arc, which means that the O and B stars must have formed, namely in the spiral arcs. So O and B associations trace out the nearby segments of spiral arms. But other method allows astronomers to map spiral arms across the entire galaxy. The dust clouds that block the view at visual wavelength are transparent at radio wavelength, because radio waves are much longer than the diameter of the dust particle. If you pointed a radio telescope at a section of the Milky Way, you would receive 21 centimeters radio signal coming from cool hydrogen in spiral arcs at various distances across the galaxy. Unfortunately, the signals can be unscrambled by measuring the droplet shield of the 21 centimeter radiation. In the direction toward the nucleus, however, the orbital motions of gas clouds are perpendicular to the line of sight, and all the radial velocities are zero. That is why the radio map shown in this figure reveals spiral arms throughout the disk of the galaxy, but not in the wedge-shaped region toward the center. Okay? The analysis of the 21 centimeter radial velocity data requires that astronomers estimate the orbital velocity of the cloud at different distance from the center of the galaxy, because these velocities are not precisely known, and because turbulent motions in the gas distort the radial velocities, and you can't trace a perfect spiral pattern in figure A into the left part of this slide. The radio map does, however, show that our galaxy has spiral arms. Also, it is hard to make out the overall pattern. From radio and visual observation, astronomers conclude that the spiral arms are rather irregular and are interrupted by branches, spurs, and cones. The stars in Orion, for example, appear to be a detached segment of a spiral arm, a spur. There are significant sources of error in the radio mapping method, but many of the irregularities along the arms seem real. And images of nearby spiral galaxies show similar features. Look at the figure B on the right side of this one. Studies comparing all the available data on our galaxy's spiral pattern with patterns seen in other galaxies do not necessarily agree with each other. Also, the newest model suggests that the nuclear bulge in our galaxy is elongated into a bar. Look on the figure A. And that the spiral arms spring from the ends of the bar. You will see in the next part of our lecture that such bars are common in spiral galaxies. The most important feature in the radio maps is easy to overlook. Spiral arms are regions of higher gas density. You have seen earlier that the arm contains young objects, suggesting active star formation. Radio maps confirm this suspicion by showing that the material needed to make stars is abundant in spiral arms. Having mapped the spiral pattern, you can ask, what are spiral arms? You can be sure that they are not physically connected structures, such as the bands of magnetic field holding the gas in place. Like a kite string caught on a spinning top cap, such arms could be wound up and pulled apart by the differential rotation within a few tenths of millions of years. Yet spiral arms are common in disc-shaped galaxies and must be reasonably permanent features. The most prominent theory since the 1950s is called the density wave theory, which proposes that spiral arms are waves of compression rather than like sound waves that move around the galaxy, triggering star formation. Because these waves move slowly, orbiting gas clouds overtake the spiral arms from behind and create a moving traffic jam within the arm. The density wave is a bit like a traffic jam behind a truck moving slowly along a highway. Seen from an airplane overhead, the jam seems a permanent, though slow-moving feature. But individual cars overtake the jam from behind, slow down, move up through the jam, wait their turns, pass the truck, and resume speed along the highway. So, do clouds of gas overtake the spiral density wave, become compressed in the traffic jam, and eventually move out in front of the arm, leaving the slower moving density wave behind. Mathematical models of this process have been very successful at generating spiral patterns that look like those seen in the Milky Way galaxy and other spiral galaxies. In each case, the density wave takes on a regular two-armed spiral pattern that bends outward from the nuclear bulge to the edge of the disk. Such spiral arms will be stable for 1 billion years or so. The differential rotation does not wind them up because they are not physically connected to the structure. As you would expect, star formation occurs where the gas clouds are compressed. Stars pass through the spiral arm unaffected, like bullets passing through a wisp of fog. But large clouds of gas slam into the spiral density wave from behind and are suddenly compressed. You saw in an earlier lecture that sudden compression of a cloud could trigger the formation of stars, and thus new stars form along the spiral arc. The brightest stars, the O and B stars, live such short lives that they never travel far from their birthplace and are found only along the arc. Their presence is what makes the spiral arms glow too bright. Lower mass stars, like the sun, live longer and have time to move out of the arc and continue their journey around the galaxy. The sun may have formed in star clusters about 5 billion years ago, when a gas cloud smashed in a spiral arc. Since that time, the sun has escaped from its cluster and made about 20 trips around the galaxy, passing through spiral arms many times. The density wave theory is very successful in explaining in ex, uh, the, very successful in explaining the properties of spiral galaxies. But it has two problems. First, what stimulates the formation of the spiral pattern? Some process must generate the spiral arms in the first place. But the pattern must also be re-stimulated, or it would die away over a few billion years. Mathematical models show that the galaxy is naturally unstable to certain disturbances, just as a guitar string is unstable to certain vibrations. A sudden disturbance, the rumble of a passing truck, for example, can set the string vibrating at its natural frequency. And similarly, minor fluctuations in the galaxy's disk or gravitational interactions with passing galaxies must generate a density wave. The second problem with the density wave theory is that it does not account for the branches and spars observed in the spiral arms of some galaxies. Computer models of density waves produce regular two-armed spiral patterns. Some galaxies, called grand design galaxies, do indeed have symmetric two-armed patterns, but others do not. Some galaxies have a great many short spiral segments, giving them a fluffy appearance. These galaxies have been termed flocculent, meaning woolly. Our galaxy is probably intermediate between these two types, between woolly and fluffy. How can astronomers explain these variations? Perhaps The solution lies in a process that sustains star formation once it begins. Star formation is a critical process in the creation of the spiral pattern. It only makes spiral arms visible, but it may also shape the spiral pattern itself. The spiral density wave creates spiral arms by the gravitational attraction on the stars and gas flowing through the arm. Even if there were no star formation at all, rotating these galaxies could form spiral arms. But without star formation, to make young, hot, luminous stars, the spiral arms would be difficult to see. It is the star formation that lights up the spiral arms and makes them so prominent. And thus, star formation helps determine what you see when you look at a spiral galaxy. But star formation can also control the shape of spiral patterns in the birth of stars in a cloud of gas, and can trigger the formation of more new stars. Consider a newly formed star cluster with a single massive star. The intense radiation from that hot star can compress nearby parts of the gas cloud and trigger further star formation. Also, massive stars evolve so quickly that their lifetimes last only an instant in the history of a galaxy. When they explode as supernova, the expanding gases can compress neighboring clouds of gas and trigger more star formation. Examples of such self-sustaining star formation have been found. You saw in the lecture on star formation that the Orion complex consists in the Great Nebula in Orion, and the star formation buried deep in the dark interstellar cloud behind the nebula is such a region. Self-sustaining star formation can produce growing clumps of new stars, and the differential rotation of the galaxy can drag the inner edge of the clump ahead and let the outer edge lag behind to produce a cloud of star formation shaped like a segment of a spiral arc, a star. Mathematical models of galaxies feel to be such segments of spiral arc do have a spiral appearance, but they lack the ball. Two-armed spiral that astronomers refer to as a grand design spiral pattern. Astronomers suspect that self-sustaining star formation can produce the branches and spars so prominent in fluorescent flocculent galaxies. But only the spiral density wave can generate the beautiful two-armed spiral pattern. And this discussion of star formation in spiral arms illustrates the importance of natural processes. The spiral density wave creates the graceful arm, but it is star formation in the arms that makes them stand out so prominently. Self-sustaining star formation can act in some galaxies to modify the spiral arm and produce the branches of spark. By searching out and understand the details of such natural processes, you can begin to understand the overall structure and evolution of the universe around us. Thank you for listening and watching this video. As usually, if you have any questions or propositions, you leaving it under this video. I hope you enjoyed this lecture, and as usually, I'm looking forward to seeing you next time. Bye.